Okay, so the next topic is SSL or TLS or the HTTPS. Basically, this is the lecture where we will see all the cryptographic protocols we covered previously in action. Okay, where exactly, how they all fit in the same picture, and provide all the services in SSL. This is the most common and secure protocol. Yeah, so SSL and TLS, they basically mean the same thing. SSL is secure socket layer, TLS transport layer security. Basically, SSL was developed in Netscape company and browser. Version. So it evolved into TLS specified in RFC 2246. So basically, TLS can be viewed as SSL version 3.1, and the difference is really very small. Okay, so when you say SSL and TLS, it's a small detail, very not that important detail. Basically, they just changed the name. So they mean the same thing. SSL, TLS mean the same thing. And where we use it, so basically HTTPS is you combine HTTP plus TLS, you obtain HTTPS. Okay, so it's HTTP, but all the payloads are protected with the TLS protocol. Okay, so it stands between the transport and the application layer. So all the data at the transport layer will be processed before it reaches the application layer with SSL. So SSL is designed to provide security and compression. So this is the main design goal of SSL. It provides not only security with all confidentiality and integrity, etc. It also provides compression services. Okay, but in current use, in these days use, compression is not really used because networking capabilities or the bandwidth of networks is good enough, and we don't really need compression. Okay. These are the SSL services. So fragmentation, compression, message integrity, confidentiality, and framing. Fragmentation, what does it mean? Split it into fragments. Okay. Compression, basically, it has a feature to compress some blocks or packets. Message integrity, we know what it is. Confidentiality, we know what it is. Framing. What makes it different from fragmentation? Framing, what does it mean? Yes. So framing, basically, for each block, you will add a header to make a frame. Okay, so there is what we call HTTPS header. Now, SSL uses a lot of cryptographic protocols, and basically, when we need to encrypt data, we need three things. Basically, we need a way or protocol for symmetric key cryptography. Here we start. The first thing, we need a protocol for key exchange. Okay, so you need to specify one protocol for key exchange. You need one protocol for digital signature. Okay, so you need protocol for digital signature, and digital signature meaning an asymmetric cryptographic protocol. And then we need, of course, the symmetric key cryptography, the encryption protocol. So before starting SSL, the two parties, the client and server, needs to agree, because you have a lot of options. And sometimes one of the party does not support one of the protocols. So he will list these, he will say, okay, these are the protocol I can use. Okay, and then they will agree, okay, on only one. Okay, so this is the key exchange algorithm. So the first one is null, basically. What does it mean, null? No, you cannot. You cannot use SSL without encryption. Okay, so null, it means there is no key exchange. What does it mean? The client and server already has agreed on a key, so they have already somehow exchanged some key. Okay, to this one, you can exchange the key with RSA, basically just encrypt. Okay, basically, one will generate the key or the secret key, the client of the server, and then it will send it to the other party by encrypting it with the public key of the other party. Okay, so just RSA, plain RSA. Then we have three versions of Diffie-Hellman. Okay, so there is anonymous Diffie-Hellman, ephemeral Diffie-Hellman, and fixed Diffie-Hellman. So in anonymous Diffie-Hellman, basically here it's the typical Diffie-Hellman where, if you remember when we covered Diffie-Hellman, it starts by having the one party sends some G, P, and R1. Okay, G and P and R1, if you remember. But they remember it's sent in clear, in plain text. So here this is anonymous. Basically, you send them in clear, and then the server will respond with also G and P and R2 in clear. Okay. What is the problem of this? This is anonymous. Anonymous Diffie-Hellman. What is the problem? Remember last time?
Error notifications.
Huh?
You can actually capture a packet and resend another reply.
So, management. It can be a target of management in the attack. Okay. So, anonymous Diffie-Hellman, when you don't use authentication of the, or you don't encrypt the packets you need to send, okay, to the party, there might be management. Okay. So sometimes the two parties might decide to use anonymous Diffie-Hellman. So basically, anonymous Diffie-Hellman, you use it when you don't have the public key of the other party. Okay. Okay. So the next one is ephemeral. Ephemeral Diffie-Hellman. Here, see here we specify RSA or DSS. These are two asymmetrically cryptography. Now, in ephemeral, basically, you will encrypt those Diffie-Hellman parameters when you send them. Okay. Remember, I think you forgot Diffie-Hellman, right?
We did it.
PQ.
It's RSA.
But it's not part of the quiz. This is why. Okay. So basically, in the first step, the client sends G and P and R1.
Yeah.
And remember, R1 how it is generated?
Modulo
G to
the power.
Huh? G to the X modulo P. So basically R1 equal to G to the power X, which is a chosen random number by C. Okay, modulo P. Okay, that's it, and it will send G and P and R1 the result. Okay, but these are sent in clear. Okay. Now the server will do the same thing and will send G and P and R2. Now this is anonymous. Now ephemeral Diffie-Hellman, basically, instead of sending this in plain, you will encrypt it with the public key of the server. So it's basically authenticated. Okay, and either the public key of the server or the private key of the client. No, the public key of the server. Why? So basically, because you need to protect that information from third party. So if you encrypt it with the private key of C here of the client, is it protected? It is authenticated, just authenticated. It's not anybody can see it. Okay. With the public key of the client. Okay. Yes.
What's the point of protecting it? We saw that we said that it's unfeasible to compute that.
Remember, man in the middle, he will not crack R1. He will not be able to retrieve X out of R1. He will not be able, even if he sees the target plane.
He'll present his one from?
No, he will put himself here. And he will open a session with this one, another session with this one. Yeah. Fixed Diffie-Hellman here, where you, the two-party client and server do not need to exchange GMP. GMP and fix it for, let's say the user are in a certain community. Okay. And let's say those community, 100 users, they fix the GMP. It's known by everybody. So you don't need to send it. Okay. So it's fixed from the beginning. And then you just need to send R1. And even R1 you need to send it to here, it says RSA or DS, means you need to encrypt it with the public key of the server. Now for Trissa, this is another, or for Tessa, this is another key exchange algorithm. Not cover it. Yeah, so null mode, there is no key, this method, no pre-master secret established between the client and so this is the null. This is the what is it? RSA. Yeah, this is using RSA to just send the pre-master secrets, the key basically. Because here in SSL, one important note, when you send the key exchange, you don't just have one key that you need to exchange. It's not just the symmetric key that you need to exchange. You need to exchange 6 keys, six of them, not just one. Okay, and they are used in several things. So basically, what you exchange the first time is a pre-master secret. This is a small secret, small random number that you will need to generate all the other 6 keys. Okay, so you exchange one secret and then you generate out of that secret 6 keys. Okay, so using RSA, basically you encrypt that the client generates that pre-master secret and then it will encrypt it with the server, the public key of the server. Okay, simple RSA. This is anonymous, Diffie-Hellman. Okay, so basically here, as I told you, send the GMP and the R1 and R2 are in plain text. You don't need to encrypt them. Ephemeral Diffie-Hellman, you will do the same thing, but you will protect the GMP and the R1 when you send them with the server public key. Okay. Yeah, the fixed Diffie-Hellman. This is, as I told you, all entities in the group can prepare fixed Diffie-Hellman parameters. Oh, okay, yeah. So they know that. They know that GMP. Okay, encryption algorithms. What kind of symmetric key protocols are used in SSL? This is the list. So null, no encryption. Okay. So no encryption here. Basically, confidentiality for some reason is not needed, but maybe authentication is needed. There is this RC4, RC2. These are other symmetric key cryptography. We did not cover them. We covered just DES and AES. Block DES. So basically here it's DES, and you see here, for example, this one, it stands for what? Triple DES. Encrypt, decrypt, encrypt. Because 3 times. So you encrypt and you decrypt and you encrypt.
This is 3DS again.
Huh?
This is the same as 3DS.
No. This is one single cipher.
Okay.
This is the algorithm. This is the way. Encrypt, decrypt, encrypt. It might be EEE. It's encrypt, encrypt, encrypt. Then CDC.
Compressor.
The other one is EBC.
Yeah, EBC, CBC. I showed you in Wikipedia. This is chained block cipher. Chained block cipher. So basically, the output of the previous block, you will use it to generate the output of the next block. Okay. So these are different for ways of using DES. There is another algorithm, IDEA, for this also. And here, by the way, as I told you, book for example, contains a lot of typos. Okay. So for example, here they didn't mention AES, which is basically part of the ciphers. Okay. The hash algorithms. You need a hash algorithm for digital signature. So you can have known, and then you have MD5 and SHA-1 or message integrity. Okay. So this is the combination of key exchange, hash, and encryption algorithms. So basically, see the asymmetric key protocols, RSA and ECC, or all that, they are used in the key exchange. They are used in the key exchange. Okay. This is an example of a string specifying all the details of the cipher. Okay, this is called the cipher. Okay, well, defines the cipher suite. Yes, for each SSL session. So basically, it starts SSL named protocol. Then this is one. Diffie-Hellman for key exchange. Diffie-Hellman. Then Diffie-Hellman with RSA for digital signature. Okay. Then with DSCBC shell. So DES chain block cipher, and then with the hash algorithm is shell. Okay. So this is enough to start and using SSL. Of course, if you specify this, you need the keys. Okay, you need to establish the keys. Okay. So these are the some list of the cipher suite supported, or the typical cipher suite that you can have in SSL. Okay. Yeah, as I said, compression is optional. As I told you, compression is not very commonly used. No specific compression algorithm is defined for SSL. Therefore, the default compression method is none. So by default, if you don't set it on by explicitly, there will not be compression. Okay. Here, we're going to use the two terms, session and connection. Okay. There is a difference between session and connection. In a session, what is the difference? Okay, before you read this. Okay, what is the difference between session and connection? There's something. Yes.
Session can have multiple. One session can have multiple connections.
Yes.
One connection. Yes, one session is a long session, and connections. Well,
this is not the main difference, but this is a consequence of the main difference. Okay. So basically, the main difference, I think, in a session, one party is a client, one party is a server. Okay. In a connection, there are two peers. Okay. So basically, in a session, you can have several connections. Yes. In a session, you might have several connections. So basically, yeah, you have a session, and then you can have several. So here, why we see the difference between session and connection? Because the key exchange is done once per session. Then when you agree on that pre-master secret, you will use it if you need to open one connection. You will use it to generate a set of keys. Now you use that connection, you use it to send, receive data in the encrypted way. Then you can close that connection. And then if you want to open another connection, you don't need to go through the key exchange again. So you will start from the same pre-master secret, and you generate another set of keys, okay, for another connection. That's it. Okay. Yeah. So these are the session state parameters: session ID, peer certificate, compression method, cipher suite, master secret, and the same thing. Agreeing on the cipher suite to be used is done only once for the state, for the session. Okay, and all the other connections you will be using the same cipher suite. So cipher suite master secret is resumable. These are the parameters for a session. Okay, the ID, the certificate type, okay, and then the compression method, if any, the cipher suite, the master secret. This is the key, or not the key, the secret. Again, you see the difference between a key and a secret. The secret is one random value that is shared in the beginning, of the session, and it will be used to generate several keys. So secret will be generated to generate, be used to generate several keys. So this is master secret. It's 48-byte secret, and is resumable if the state you can resume it once you close. So yes, close new connection in null session. Yeah. So can you have several connections in that same session? You might, for additional security, you might prefer to have it not resumable. Basically, if you need to open another connection, you will need to redo all the process from the beginning: key exchange and master secret. That's it. Now, connection state parameters. These are the state parameters, the connection parameters, not the session. Okay. So basically, in a connection, again, you don't need to agree on a master secret, for example. Okay. So what are the parameters? Server and client random numbers, the sequence of bytes chosen by the server and client for each connection. Server writes MAC secret. What is a MAC?
MAC address or?
Message authentication code. Message authentication code. Basically, the message authentication code it's a hash. It's a hash. But what makes it different? We saw it. In the hash.
Encrypted.
It encrypted. What does it mean?
There's a key.
There is a key. So you need the key. When you hash, you also have a key as input. Because just hash, you don't have a key. Okay. So server write MAC secret, client write MAC secret. So here, basically, this is one important node for SSL. For MAC, when you use the key to provide the hash or to find the hash or compute the hash. And also for symmetric key cryptography, you don't use one key for both directions. You will need, so for example, if you need something to send something in this direction, you will use key 1, K1, okay? Then you encrypt it with K1 here, and you decrypt it with K1. So basically both the sender and the receiver needs to know that key. In the other direction, if you need to send data in the other direction, you need to use another key, not the same key. Okay. This is for encryption and also for MAC, or message authentication code. Okay. Data in every direction will use a different key. See the point? Okay. So basically here you need server write MAC secret and the client write MAC secret. This is why you need two. Okay. One for client direction and one for server direction. Same thing here. Server write secret. This is the symmetric key. Symmetric key in one direction, symmetric key 2 in the other direction. Okay.
We have two symmetric keys.
Yes. Two symmetric keys. Each one for every, but they are secret. They are symmetric because they are used here and here. Okay.
But shouldn't they be the same if they are symmetric?
Yeah, they are.
Okay.
Because K1 here, you use it to encrypt and you use it to decrypt. It is symmetric.
I see.
But basically you use another key in the other direction. There is a difference.
So
Okay.
if I am the sender, I use the first key. If I am the receiver, I use the second key.
Yes, but you need both keys anyway. Because to decrypt the data coming, you need that. So this is why it's still symmetric. We didn't lose symmetric property.
What's the point of having different keys for different directions?
More security. Basically, if you have two keys to crack, basically, it's more challenging.
Sniffing will be hard.
And then you have the, as I told you, there are 6 keys generated from the master secret. Okay, so this is 1, this is 2, this is 3, this is 4. These are 4. And then you have initialization vectors. Remember in the CVC, the shade block ciphers. Okay, when basically, what does it mean chain block cipher? If you remember. So basically, the output of the previous encryption of block encryption will be used to encrypt the next block. But the problem is, for the first one, what is the input? There should be some initialization vector, and this one. So basically, you use the master secret key to generate the initialization vector, and you need one vector in one side and another vector in the other side. So this is why you need 2 initialization vectors. So basically, in total, you have 6 keys. Not just
Why
CBC. You know, CBC is not the TV channel. Right?
Shady box
CBC
cipher.
is with.
Well, it has to be private. It can't be public, right?
So here, this is your data. You split it into blocks, and then when you encrypt, so this is the encryption algorithm. We saw that every block will be encrypted separately, right? So you encrypted, you obtain a cipher here. Okay, cipher. And then you encrypt this, you obtain a cipher. Okay. Okay. Etc. Now this is basically called what?
EBC.
EBC, electronic code book. Now, CBC is chained. Basically, what you're gonna do, you will use the output of this encryption, and then before you encrypt, you XOR it with the data of the previous block. Okay, so you keep doing that. Okay, okay. But the problem is, what kind of input you need to use for the first block, because it's the first one. There is nothing before it. Okay. So here you use that initialization vector for that.
Can't this first one be public?
Which one? This one?
Like because in the block it's a
chained block cipher. Is it? No, this is in the SHA and the hashing. And the hashing is public. Okay. And even the matrices or the vectors, initialization vectors in DES and AES also, they are public in the algorithm. But for the block chaining, they are not. Okay. Okay, so I think we need to stop here. Let's finish. Yeah, so basically, so we have 6 different cryptographic secrets, 3 read and 3 write. Yeah, let's stop. Okay.